Good morning, everyone. I know there's a lot still up collecting coffee and refreshments, but to try to keep the program on some semblance of time, I'd ask everybody who's in the room to come and be seated, and we'll try to get the session going. So I'm David Salona. I'm from the University of California, San Francisco, and I'll be co-moderating this morning's session with Yi Chao, who's from Johns Hopkins. And we've got a very interesting set of invited speakers, but then also submitted abstracts from a variety of different people. And we're going to start off with Huijun Chen, who's from Tsinghua University, going to be speaking on state-of-the-art techniques of quantitative MR vessel wall imaging.
Okay. Thanks for the introduction, and thanks for the invitation. Today my topic is state-of-the-art techniques for quantitative MR vessel wall imaging. Previously, Chen has introduced why we do vessel wall, so I just skipped that. So for quantitative vessel wall, it's a little different because traditionally we all do weighted imaging. But if we switch to quantitative MR, we can not only can accurately identify all those components, but also can reflect some physiological phenomena what happens in atherosclerosis. So today my talk would be two parts. First, I want to introduce the DCE MRI work for vessel wall imaging. The second is quite traditional quantitative MR techniques used for vessel wall imaging. So DC MRI actually, in early days, by using contrast and acquire it dynamically, it has been proven to be able to quantify angiogenesis and inflammation of atherosclerotic plaques. It has been proven to be a useful tool in vivo quantification tool for physiological studies, and it also can be used to do a therapeutic response monitor or the correlation with symptoms. So the basic techniques for vessel wall DCMRI is quite traditional. We just use a traditional SPGR sequence, but first thing is it should be a bright blood. The second is it should be there should be a saturation band to ensure a black blood before the contrast arrival. And then we can acquire two curves. One curve is AIF extracted from the lumen, and another is for tissue uptake curve extracted from each pixel inside the vessel wall. And then we can use a pharmacokinetic model, such as PET-like model, to generate the K-trans and VP for each pixel inside the plaque. So, however, there are several challenges. The first one is vessel wall related. Because we use all the signals to generate high spatial resolution DCMR image, because vessel wall, the plaque is not very large. So the temporal resolution is not very well for AIF acquisition. The second is if it's bright blood, the signal contamination from the bright lumen could affect the accuracy of the quantification. To deal with that, in early days, black blood DCMRI has been proposed, basically using DIR or QIR techniques to suppress the blood. But the problem of this kind of method is there's no measured AIF. So usually they use population-based AIF, but that could introduce some bias. So let's see what the problem is. So for ideal vessel wall imaging, we need a high spatial resolution for vessel wall, but the signal change is not that fast. So we don't need high temporal resolution. And also we need black blood to eliminate the signal contamination from the lumen. But for ideal AIF imaging, we need a high temporal resolution to sample the fast changing AIF. Second is if we want to extract AIF from each patient, we need bright blood. So this is conflict. How to deal with that? There is we propose one sequence, we call it hobby, which is interleaved acquisition. We can acquire high temporal resolution AIF and high spatial resolution black blood vessel wall imaging at the same time. It can reduce the variance and error of the pharmacokinetic analysis. And this is another advanced version, we call it LABI. We further use 3D SOS acquisition to acquire, to have a larger coverage. And recently there's a technique proposed using multitasking. Basically, this is a saturation recovery multitasking technique. Amazingly, it can acquire real-time T1 mapping during the DCE acquisition. The temporal resolution can reach to 0.6 to 1.2 seconds. So another way to optimize the whole process is to deal with this AIF. So the AIF actually have some problem in traditional protocols. First is the signal saturation problem, which is caused by the T2 and the T2 star effect of the contrast agent. Because our DCE acquisition usually is T1, but the contrast agent have T2 and the T2 star effect. Secondly, it could be influenced by flow. And lastly, the sharp peak of the AIF actually require high temporal resolution to capture. So one solution is to use phase-based VIF, acquire phase to eliminate the nonlinear relationship with contrast concentration, and it can also reduce flow artifact. And the second is we develop, we use a simulation study to prove that if we inject the contrast concentration slowly, we could avoid the peak. So that means you can acquire the AIF with lower temporal resolution and still get accurate estimation of the parameter maps. So for the quantitative MR, there are many works. So I think for T1 mapping, usually for T1 mapping, T2 mapping, T2 star mapping, QSM, and DWI. The major purpose to do that is to better quantify the plaque components, such as intraplaque hemorrhage, lipid retinosine core, calcification, or fibrous. And T2 star and QSM can also quantify the ion inside the plaque, which is also a physiological marker for the severity of the plaque. However, using traditional method, there are challenges. The first one is blood suppression from vessel wall imaging. Usually we do vessel wall, we need black blood. That's the main challenge. The second one is traditional mapping techniques are using multi-scans. So there could be a misregistration among weighted imaging scans. So let's summarize for vessel wall T1 quantification. So traditionally, you can use variable flip angle, or the inversion recovery, or saturation recovery, or the look locker. So, but the problem is we need to suppress the blood. So traditional early work always use blood suppression techniques such as MSDE, or using TSE, or using immersion to suppress the blood. For T2 and T2 star quantification, it's similar. For suppress the blood, you use DIR or MSDE. Sometimes in T2 mapping, usually it's a multi-echo, spin echo sequence with different TE. For T2 star, it's usually multi-echo FFE or SPDR with different TEs. So similarly with Westerwald QSM, they have, it's quite similar to T2 star mapping. The difference is the additional acquire the phase. So I think the major point of this is to use QSM to identify IPH and calcification, because these two things are sensitive in QSM image. And there are also studies working in 2D DWI imaging of Westerwald. These two techniques are 2D techniques, and these techniques are 3D techniques. So in recent years, I think the area every researcher has focused for this quantitative Westerwald imaging using one scan. This is published in radiology from our group. We developed this sequence called GoSnap, which is basically an inversion recovery plus a 3D golden angle radio sampling. Because it's a radio sampling, we can acquire different weightings just by reconstruction. So you can see from here, our sequence is quite fast and in one scan. And and we also develop deep learning enhanced reconstruction method for this technique. It can further reduce the scan time and fitting time. And there are other groups working in T1 and T2 star complication in one sequence. Basically, this is also a inversion recovery sequence, and plus multi-echo with different TEs to quantify T1 and T2 mapping. And we, our group also developed this T1 and T2 quantification in one sequence. We call it simple. It's a T2 IR plus 3D golden angle radio acquisition. And in this year, we published this new techniques we call this simple star. It's also T1, T2, and T2 star quantification in one sequence. Notably, all those sequence is initially for quantification Westerwald, but actually because it can generate multi-contrast from it, so we can get non-contrast MRA and also T1, T2 weighted imaging from this quantitative imaging sequence. And this is a similar work using multitasking. We can generate bright blood, black blood, and gray blood from their multitasking sequence. One thing I want to add is currently a lot of work is focused on not only on carotid artery, but also for intracranial artery, intracranial plaques. These two works, one on 3T and one on 7T, are all ex vivo works. And it actually showed that the intracranial plaque also are very complex with different components. And our group initially tried this intracranial Westerwald imaging. Firstly, we tried our GoSnap in intracranial Westerwald T1 mapping. And last year, we have tried this T2 star mapping on 7T, but it's quite this one using a quite traditional scan protocol. So as a summary, the DCMRI can quantify the inflammation and angiogenesis in plaque, and the technical advances can improve the accuracy and reliability. And secondly, for multi-parameter quantitative imaging in one sequence currently is a trend. It can generate quantitative images, but also can generate weighted images, even with MRA. And such as the multitasking, our go snap simple and simple start sequence. Probably MRF can also be used. And this could be the next generation plaque imaging mainstream protocol because it's simple and the scan time is shorter and it's suitable for post-processing because there is no misregistration among them. And lastly, vessel wall imaging, quantitative vessel wall imaging currently is from carotid vessel wall, currently is developed to intracranial plaques. And I hope we can have a good result. So that's all my presentation. Thanks.